All right, in the second part of 3.4, we are going to take everything that we talked about in the last video and put that together to solve a few problems. Okay, so here we have a 7-step process to finding the zeros of a polynomial. Okay, so the first is just to consider the degree of the polynomial. Right, the degree of the polynomial tells me the maximum number of real zeros that I would be looking for. If we have a fifth degree, we could have up to 5 real zeros. Step 2 is use Descartes' rule of signs to find the possible number of positive and negative zeros. Then use the rational roots theorem to find the set of possible rational roots. Remember, that was just taking all of the factors of the constant over all of the factors of the leading coefficient. And then we start testing. Okay? We just start plugging numbers in using synthetic division. Okay? Generally, we start with the smallest positive integer from our list, and usually that's 1. Okay? And then we just keep testing until we find a 0 or an upper bound. Okay? Then, once we have exhausted the positives, then we will test negatives. Right? Looking for negative roots or lower bounds. And then once we get down to a quadratic, we have multiple ways that we can solve a quadratic, right? We could potentially factor it or use the quadratic formula. Right? So let's just go through a couple of examples using this process. Right? So my first example here is a fifth degree polynomial. That means I could have up to 5 zeros. All right. So first, let's use Descartes' rule of signs to determine how many positive and how many negative zeros we could end up with. So remember, to test for positive zeros, we look at how many variations of sign there are. So for f of x, whoops, I am starting with a positive, then a negative, negative, positive, positive, negative. So one change of sign, two change of signs, three change of signs. Okay, there are 3 variations of signs in f of x. So that means I could have 3 positive zeros, or remember, we could subtract by an even amount. So I could have 3 or 1 positive zeros. Right? Then, to test for negative zeros, we plug negative x in. So f of negative x would be 2 times negative x to the fifth minus negative x to the fourth minus 14 times negative x cubed plus 7 times negative x squared plus 24 times negative x minus 12. So whenever we have a negative to an odd root, that will remain negative. Right? So this would be negative 2x to the fifth. Whenever we have a negative to an even root, it becomes positive. So this would just be minus positive x to the fourth. Then this would be negative. So we actually have a double negative here. That would become positive. This would stay positive, right? Negative to an even power. This would be negative minus 24x minus 12. So now if we consider the signs, we go negative, negative, positive, positive, negative, negative. There's only 2 places where I change signs, right? Where there's a variation in sign, right here and right here. So that means that my function has either 2. Again, we can subtract an even amount. So either 2 or 0 negative zeros. Okay, so now we want to list our possible rational roots, right, or possible rational zeros. We abbreviated it like this on our last set of notes. So that's where we take all of the factors of the constant over all of the factors of the leading coefficient. So the factors of 12 would be 1 and 12, 2 and 6, and 3 and 4, right? And remember, we take the positive and negative of all of those. And then over all of the factors of 2. So that's just 1 and 2. So if I list those out then, I'll list all of these over 1 first. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, and then list all of them over 2. So plus or minus 1 over 2. Then we have plus or minus 2 over 2, but 2 over 2 is 1, which we already have listed, so I don't need to list it again. Then plus or minus 3 over 2, then plus or minus 4 over 2, but 4 over 2 is 2, and we already have that listed. Then plus or minus 6 over 2, well, that's just 3, we already have that listed. And then plus or minus 12 over 2, which is just 6, and we already have that listed. So this would be my entire list of possible rational zeros. All right, so step 4 said to take the smallest positive integer and test it using synthetic division. So my smallest positive possible rational zero is 1. So I'm going to test 1 here. List out my coefficients. So that's 2, negative 1, negative 14, 7, 24, and negative 12. All right, so bring the 2 straight down, multiply, add, multiply, add, multiply, add, multiply, add, multiply, and add. So we get 6. Since my remainder is not 0, 1 is not a root. So we'll just go to the next positive integer. Let's try 2. All right, so again, list out my coefficients. 14, 7, 24, negative 12. And synthetically divide. So bring the 2 down, multiply, add, multiply, and add, multiply, and add, multiply, and add, multiply, and add. We get a remainder of 0. That means that 2 is a root. Okay, so my depressed polynomial, since I started with a 5th degree, this depressed polynomial would be 2x squared, or I'm sorry, 2x to the 4th. Since I started with a 5th degree, we just go 1 degree down. So plus 3x cubed minus 8x squared minus 9x plus 6. And now I just want to continue the process. Okay, I have not found an upper bound yet, right? But I can try now plugging in 2 again. Right? It is possible that 2 could be a repeated 0. So I want to take these coefficients of my depressed polynomial and try plugging 2 in again. Right? So if I list out these coefficients now, again trying a 0 of 2, that'll be 2, 3, negative 8, negative 9, 6. So bring the 2 down, multiply, add, multiply, add, multiply, add, multiply, and add, and we get 12. So that means that 2 is not a repeated 0, okay? It only shows up once. However, I did gain some information from this. If we remember our rules for bounds, if everything in the final row ends up being positive or 0, that means that this value was an upper bound. So 2 is an upper bound. I can discard all of the possible rational zeros greater than 2. Okay, so if we look back at our list, I can get rid of 3, 4, 6, and 12. Okay, anything greater than 2 I can get rid of. Right, so let's make a note here that we found 2 was an upper bound. So we only have a few more positive zeros that we could try. Okay, we have 1/2 and 3/2. So let's try those here. And if we plug 1/2 in, and again, we can use these coefficients here, right? So we'll have 2, 3, -8, -9, and 6. Bring the 2 down, multiply, add, multiply, add, multiply, add, multiply, and add. And we find that 1/2 is also a root. Okay, so we've got 2 roots already. Okay, and maybe I should highlight these. So let's say we found that 2 was a root, and we found that 1/2 was a root. Okay, so now that means we are down to a third degree polynomial. Since this was a fourth degree, this would be depressed down to a third degree. I've got 2x cubed plus 4x squared minus 6x minus 12. Okay, so now we can try some of our other values. All right, so let's try 3/2. All right, let me extend the page a little bit. So let's do 2, 4, -6, and -12. So if I bring the 2 down, 3/2 times 2 would be 3. Add, multiply, that'd be 21 over 2. Add, so that would be 9 over 2. This isn't looking too promising, is it? So multiply, that would be 27 over 4. So 48. That would be -21 over 4. So 3/2 is definitely not a root. We have actually exhausted all of our positive possibilities because we found 2 was an upper bound. Okay, so let's start using our negative roots. Right, so first, let's try -1. Okay, generally we'll start with the greatest negative root and work our way down. So again, we're using our coefficients here: 2, 4, -6, and -12. All right, bring the 2 down. -1 times 2 is -2. Add, multiply, add, multiply, add, and we get a remainder. That means that -1 is not a root. So let's try our next value. Let's try -2. So again, 2, 4, -6, and -12. Bring the 2 down. -2 times 2 is -4. Add, multiply, add, multiply, add, and we get 0. So -2 is a root. We have now found 3 roots. And since this was a third degree, that means this is depressed all the way down to a quadratic. This would be 2x squared plus 0x minus 6. Now I can finally take this quadratic and solve. All right. So I can just add the 6 over, divide by 2, get x squared equals 3, and then just take the square root of both sides, and I get x equals positive and negative square root of 3. Don't forget, whenever you take a square root, you get a positive and a negative. I have now found 5 roots. Since my maximum number of roots was 5, I know for sure that I've found all of them. So, my answer to this problem was, and generally we want to write them in order, right? In order of magnitude. So negative 2 would be the smallest, then negative square root of 3, then positive 1/2. Get rid of that little dot there. Then next up would be positive square root of 3 and 2. These are all of my roots of this 5th degree polynomial, right? These problems are a lot of work, right? That was a lot of guessing and checking, a lot of making sure. And if we look all the way back to what we found originally, our using Descartes' rule of signs, we found 3 positive roots and 2 negative roots. So that rule fits, right? Now, let's try another example here. This one is a 4th degree. Okay, so again, let's start by using Descartes' rule of signs. So first I guess, I'm sorry, let me back up a step. First, take a look at, this is a 4th degree polynomial. That means that we will have at most 4 real roots, okay? Now let's use Descartes' rule of signs. So the first term is positive, then negative, then positive, then negative. I can see I have 1, 2, 3 variations in sign. That means that I have either 3 or 1 positive roots. Now, let's evaluate f of negative x. So 3 times negative x to the 4th minus 11 times negative x cubed plus 22 times negative x minus 12. And that would be, so again, a negative to an even power would become positive, so 3x to the 4th. A negative to an odd power will stay negative, so we actually have a double negative here. That would become plus 11x cubed minus 22x minus 12. So my signs are positive, positive, negative, negative. I only have one variation in sign here, so that means I have one negative root. All right. Next step is to list out our possible rational zeros, and that is all of the coefficients, or I'm sorry, all of the factors of the constant over all of the factors of the leading coefficient. So all the factors of 12 would be 1 and 12, 2 and 6, 3 and 4, just like the last problem. And those are all over the factors of 3, which would be 1 and 3. So here, again, first I'll list all of these over 1. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. And then I want to list all of these over 3. So that'll be plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, Then plus or minus 6 thirds would be 2, and plus or minus 12 thirds would be 4. And we have both of those already listed. So this would be my entire list. So now let's try plugging some of these in and seeing what we get. So let's start with our smallest positive root. That would be 1. List out the coefficients here. But notice we are missing an x squared term. I need to put in a 0 placeholder for the x squared. Don't forget that step whenever you're synthetically dividing. All right, so bring the 3 down, multiply, add, multiply, add, multiply, add, multiply, and add, and we get a remainder of 2. 1 is not a 0, and we can't determine anything here as an upper bound. So let's move on to our next positive possible rational 0. That would be 2. So again, list these out. 3, negative 11, 0, 22, and negative 12. Bring 3 down, multiply, add, multiply, add, multiply, add, multiply, add. 2 is not a 0 either. All right, let's try our next one. Let's try 3. So 3, negative 11, 0, 22, and negative 12. Bring the 3 down, multiply, add, multiply, add, multiply, add, multiply, and add, and we get a remainder of 0. That means that 3 is a root. And we now have a depressed third degree polynomial since we started with a fourth degree. This would be 3x cubed minus 2x squared minus 6x plus 4. Okay, so let's try 3 again. Right? It could be a repeated 0, so let's try it again. So now I can use these coefficients. Okay? I can use 3, negative 2, negative 6, and 4, the coefficients of my depressed polynomial. Bring the 3 down, multiply, add, multiply, add, multiply, add. And this is definitely not a 0, but I do get an important piece of information. Since all of these entries are positive, that means 3 is an upper bound. I can discard everything on my list greater than 3. Okay, so since we know we have, either 3 or 1 positive root, there's going to be some more. So, well, I guess not necessarily more. We could only have 1, okay? But let's keep trying our positive roots here. So I already tried 1, 2, and 3, and I can discard everything greater than 3. So let's try some of our fractions. Okay, let's start with 1/3. All right. So, and again, I'm using the coefficients of my depressed polynomial here. So negative 2, negative 6, and 4. Bring the 3 down, multiply, add, multiply, add. So that would be negative 19 thirds, multiply. And this is definitely not going to get us anything. So that would be 5/6. All right. No information there. 1/3 is not a root. So let's try 2/3. 3, -2, -6, and 4. Bring the 3 down. 2/3 times 3 is 2. Add, multiply, add, multiply. That would be -12 over 3 would be -4. And add, and we get 0. So 2/3 is a root. We have now found two roots. And since this was a third degree, that means my depressed polynomial here is a quadratic. This will be 3x squared plus 0x minus 6. And I can just solve this. So again, just like the last one, if I just set this equal to 0, all I need to do is add the 6 over, divide by 3, and take the square root. And we will get positive and negative square root of 2. So I end up with 4 answers here. Highlight these. And again, the general convention is to list them from smallest to largest. So negative square root of 2 would be my smallest root, then 2/3, then positive square root of 2, and then 3. 4 roots for my fourth degree polynomial. Okay, and again, these are a decent amount of work. There is some guessing and checking involved. Okay, and again, if we look back at Descartes' rule of signs here, we ended up with 3 positive roots and 1 negative root. All right, let's do one more example here. All right, this one is just going to be a third degree, but we are going to graph this. Okay, so to start, we want to do the exact same thing that we've been doing. We want to use Descartes' rule of signs. So I'm going positive, negative, negative, positive. I see I have 1, 2 variations in sign. So that means I have either 2 or 0 positive roots. And then if I plug negative x in, f of negative x would be 2 times negative x cubed minus negative x squared minus 4 times negative x plus 2, which would be, since that's an odd power, that'll be negative 2x cubed. This is an even power, so that would become x squared, but we're subtracting, so that would be minus x squared. Double negative here, so that'll become plus 4x plus 2. So I go negative, negative, positive, positive. Only one time that the sign changes, so that means I have 1 negative root. All right. Now let's list out our possible rational zeros. And this is actually going to be a pretty short list because my constant is 2, so the only factors of 2 are 1 and 2. And my leading coefficient is also 2, so the only factors there are 1 and 2. So if I list all of these out, I'll first list these over 1, so plus or minus 1 over 1, plus or minus 2 over 1. Then list these over 2, so plus or minus 1 over 2, and plus or minus 2 over 2 is just 1. So I only have 6 possible rational zeros here, right? Again, we want to start with 1, our smallest positive root, and list out my coefficients. So that will be 2, -1, -4, and 2. Bring the 2 straight down, multiply, add, multiply, add, multiply, and add, and we do not get 0. We get -1. Okay, so let's try our next one. Let's try 2. And if I plug 2 in, so 2, -1, -4, 2, bring the 2 down, multiply, add, multiply, add, multiply, and add. And we do not get 0 again. We get -2. So let's try 1/2. So 2, -1, -4, and 2. Bring the 2 down. So multiply, add, multiply, add, multiply, and add. And we get 0. So 1/2 is a root. We now have a second degree. This would be, since I started with the third degree, this would be 2x squared plus 0x minus 4. So if I set that equal to 0, I can just solve this quadratic. Add the 4 over, divide by 2, and take the square root, and we'll get x equals plus or minus the square root of 2. So I end up with 3 roots here, right? X equals negative square root of 2, 1/2, and positive square root of 2. Now, I want to take this information and graph my polynomial. Okay, this is kind of what we looked at in the last section. Once I know my zeros and I know the end behavior, I can sketch a nice graph. These zeros all only showed up once. That means my polynomial is going to cross the graph at each of these. So the square root of 2 is about 1.4. So negative square root of 2 would be about here, and then 1/2, and positive square root of 2. So these are my 3 zeros. Now, I need to think about end behavior to sketch a graph. My leading coefficient is positive, and this is an odd degree. So positive odd degree, we said as x goes to negative infinity, so does f of x. And as x goes to positive infinity, f of x goes to positive infinity. From that, I can sketch a rough sketch of my graph. Okay. Now, there is a little bit more that we can do here. Okay, there's one other big thing that we can take away. We can easily find the y-intercept. So if I look at this function, right, and I plug in 0 for x, I would get 0 minus 0 minus 0 plus 2. Well, that means that the point 0, 2 has to be on my graph. Okay, that's another important piece of information that we could use to sketch this graph. So, right, if we use all of that here, we can sketch a graph that, oops, that follows. And I'll probably do something like that then. So let me erase this. Okay. So there is a nice rough sketch of my graph with the correct zeros, the correct y-intercept, and the correct end behaviors. All right. I know these problems are very long, right? So there's not going to be too many for homework. Um, the final question is going to pop up here asking you what questions you have.